Hello viewers, welcome back to this channel. So in this video we are going to be proceeding with the fourth video under transition chemistry. So this fourth video is going to be elaborating the chemistry of iron as one of the components or elements under transition elements. So this video is presented to you by Olgimbe Yusuf, and the advice subscribe to the channel and share the video to your friends so that you can all benefit as a group. Now, starting with the chemistry of iron, we are going to be starting with extraction that can be involved under iron. So in this video, or in this elaboration, we are going to first talk about how our transition element, which we are going to be covering in this video, iron, can be extracted from the different ores. But one of the major ores, but one of the main commonly used ore to extract iron is called hematite. Now remember that you also cover this extraction at your O level. So what we do here is to provide details on how we can further extract it with all the materials and all the chemistry known in place. So we're going to start by saying that when you're handling extraction of iron, we are going to be using the chief ore from which iron is extracted, which is known as hematite. Now another name for hematite, or the chemical name, is known as hematite is the same as iron 3 oxide. But since it's an ore, that means that it has other impurities in it. That's why we call it hematite. Now, it's not only hematite we extract iron, but we also extract iron from other ores. And these ores are going to include magnetite, which is the same as tri-iron tetraoxide. And we can concentrate this using a magnetic field. Now remember that it's only the concentration process that's going to vary all over these ores, but the other procedures are going to remain the same. What varies is going to be the concentration process. So the other ore is going to be iron pyrites. Now iron pyrites is the same as iron 2 sulfide or iron 4 sulfide, and this can be concentrated by froth flotation. Now before we even begin, majority of you make a mistake with this spelling. The spelling of froth flotation, we don't have a. Majority of you write float, like this floating of water. We do not have a in the word froth flotation. Now that's where a majority of you make the mistake from, and that's why you lose marks from when you submit your papers for marking. Reason being, also your teachers fail to recognize that mistake. So you make sure that you correct that spelling when you are presenting your notes. If at all you have already covered these notes and you are looking for concise notes from my channel, make sure that you can edit your notes and you have froth flotation without a flotation. You need to be very eager about the spelling of this word. I'm not overemphasizing it, but it's one of the main reasons why majority of you fail extraction. Now the other ore is going to be siderite, or which is also known as spathic iron. Now spathic iron is the same as iron 2 carbonate, and it's concentrated simply by roasting it in air. Remember that when you roast iron 2 carbonate in air, you are most likely to get iron 3 oxide. You would have got iron 2 oxide, but iron 2 oxide easily oxidizes in excess oxygen to give us iron 3 oxide. And then the other procedure is going to follow the procedure that you are going to see when you're extracting iron using hematite. Now let's start by the extraction, or let's look at the extraction procedure. But here we are going to look at the ore which is majorly commonly used, which is going to be hematite. So in this we are going to say that let's look at the extraction of iron from hematite as its ore. And I'm going to start by saying that we start by the concentration process. So we are going to start by saying that the ore is going to be crushed into small particles, which are then roasted in air. And we do the roasting so as to drive out water and other volatile impurities, as well as oxidizing some of the iron 2 oxide present in it to iron 3 oxide. Now remember that I said that the ore is always impure. So that means that since we get it from the environment, it may be hydrated. So we roast it, we crush it and we roast it to remove the water of hydration. And also, since it's impure, we expect that it has some component of iron oxide. So the roasting or the heating is to help convert the iron oxide into iron 3 oxide. Now the next procedure we're going to look at is a mixture of the roasted ore together with coke coke is the same as carbon, and limestone is the same as calcium carbonate, are going to be fed into the blast furnace from the top, just like you looked at this diagram in your O level. But at A level, the diagram is not required. So after that, we are going to say that hot compressed air is going to be driven into the furnace straight away from the bottom. Now, when we press hot concentrated air, it's like burning. It's like burning this mixture that you have placed at the top of the furnace in dry air. So that's why we place hot concentrated air. But this, remember that we place a mixture of coke, carbon, and limestone. Of our ore, the coke or carbon and limestone at the top, and we are putting hot compressed air. In other words, we are putting air together with heat at the bottom of the furnace. So what happens is that coke, since it's the most easily to be burnt, coke will burn in this hot air so as we can form carbon dioxide. Remember that whenever we burn carbon in excess oxygen, we form carbon dioxide. So that's the meaning for this statement. So coke burns in the hot air so as we can form carbon dioxide. Now for us to maximize our marks when you are presenting extraction procedures is that for each and every statement that you have written requiring an equation, it has to be well stated. And the statement before that equation must contain the reactants together with the products, just like I've been over mentioning the other videos. When you're doing out the procedures, make sure that you mention both the reactants and the products, and also the conditions that are going to be required before writing an equation. So our coke, which is the same as carbon, burns in the hot compressed air to give us carbon dioxide. Balancing, I told you, start with carbon, and then you balance oxygen. Lastly, like following the procedures that you have been overlooking at in the previous videos. So proceeding, we are going to say that as the carbon dioxide is rising up the furnace, it's going to be reduced by the unburnt coke. Remember that the coke is up the furnace. So this carbon dioxide which is being formed, it ascends up the furnace. So the more it ascends up the furnace, it reacts with the unburnt coke. And when they react with the unburnt coke, reduction takes place because carbon or carbon monoxide, both of them are reducing agents. So carbon reduces carbon dioxide to carbon monoxide gas. So the carbon monoxide gas which is being formed, it's then going to reduce the iron ore to form molten iron in the upper parts of the furnace, because that's where we placed our mixture. So carbon monoxide gas is a reducing gas, reacts with iron 3 oxide, which is present in our ore. Remember that an ore is a mixture of components. It has the ore which we need, it has the hematite which we need together with the other impurities. So when carbon monoxide reacts with iron 3 oxide, reduction takes place. It reduces it to its element. It takes out all the oxygen from it. And the same applies to manganese. Such reactions are always reducing reactions. When you see reaction between carbon monoxide and N oxide, or ammonia and N oxide, or hydrogen and N oxide, all those ones are reducing gases. They reduce the respective oxides to give individual elements of what they are reducing from an oxide to the element. So carbon monoxide reduces iron 3 oxide to give us an iron solid, and later for it gets oxidized to carbon dioxide gas. Like I said, if you are to review the rules that I told you to follow when you are balancing equations, you start with the metal. So iron this side is 2, so we have to put here 2 here so that we can balance iron, and then later we balance carbon. So if you look here, carbon is 1 and also carbon is 1, assuming that the 3 was not there before. Now balancing oxygen, if you look this side, we are having 3 oxygen, and here we had initially 1. So that means that this side we had a total of 4. Now we placed here 3. Reason being that for us to balance up this, that means that we need to balance up the carbon atoms. So we simply get the number of oxygen atom which is present on our oxide, and we put, now here initially it would have been a 3/2. but we put here 3 so that we can balance. We can only consider the oxygen atoms that are present on our iron oxide, and then later we put a 3 to balance the carbon, which will eventually balance our carbon monoxide gas as a whole. Now proceeding, we are going to say that limestone is going to decompose to give us calcium oxide and carbon dioxide. Now just like any other carbonate, apart from group 1 carbonates, every carbonate decomposes to give us an oxide together with a carbon dioxide gas. So you need calcium carbonate. So condition is heating calcium carbonate to give us calcium oxide together with carbon dioxide gas, and the equation will be well balanced. Now proceeding, I'm going to say that calcium oxide is going to react with silicon oxide. Remember that silicon oxide is the same as silica, which is also an impurity which is found in hematite. And silicon oxide or silica is a major impurity found in majority of the ores that are present in chemistry, because for it exists everywhere in most of the ores. So calcium oxide reacts with this silica as the impurity to form molten calcium silicate, which is also called slag. So molten calcium silicate is formed as a result of reaction between calcium oxide from the decomposition of calcium carbonates together with the reaction of silicon oxide, which is also known as silica, present as an impurity in our ore. Now by reacting, they give us a molten liquid which is called slag, or you can call it its name of calcium silicate. Now to make a conclusion of the other extraction before, you can say that calcium silicate is later dropped off at the bottom of the furnace, and the iron or the molten, remember that the molten iron was formed first and calcium silicate is going to be above that molten iron. So we tap off calcium silicate and then we remain with iron at the bottom of the furnace, which is going to be our pure iron, and that's how we extract our iron as a transition element. Now let's look at the reactions that can be undergone by iron. Now with the first reaction, we're going to start with the reaction with water, and we're going to say that when heated, remember that iron does not react with cold water, so there must be conditions for iron to react. And I told you that before making any statement to an equation, you have to make sure that all the conditions are presented as required. That's why I was underlining them when I was providing them in this video. So heated iron, for iron to react with water, first of all it has to be heated as one of the conditions. So heated iron reacts with steam to form tri-iron tetraoxide together with hydrogen gas. Just like I've been over mentioning, whenever you are presenting a statement for an equation, you make sure that conditions are properly mentioned, and also the products you are forming are properly mentioned. Do not give the colors of the products. You just mentioned conditions together with the products being formed. So iron reacts with steam to form tri-iron tetraoxide together with hydrogen gas. Now looking at the balancing of this equation, assuming that these coefficients were not there, we only know that iron reacts with water or steam when heated to form tri-iron tetroxide together with hydrogen. So we said that we start by balancing metals. If you look this side, we're having 3 atoms of iron. So that's why I placed the 3 here, opposite iron. Then secondly, we balance oxygen before we balance hydrogen. In any equation, hydrogen is the last element or atom to be balanced. So balancing hydrogen this side, or balancing oxygen, here we had 4, so we put here 4 on water so that we can balance up the oxygen atoms on the left hand side with those of the right hand side. Now we have to balance hydrogen. So if you look at your left hand side, you're having 8 hydrogen atoms. This side we had only 2, so that's why I put here 4 so that we can balance the hydrogen atoms. So in your balancing, you start with the metals, you go to the non-metals other than oxygen and hydrogen, and then oxygen is balanced second lastly, and hydrogen is balanced as the last atom or element. Now let's go to the reactions that are involved with air. Now you're going to say that heated iron reacts with dry air to form tri-iron tetraoxide. So if oxygen is present in excess, now remember that we're using reversible arrows, because whenever we are forming tri-iron tetraoxide, it's a very unstable product. That's why we are using reversible arrows. It can easily decompose back to give the respective reactants. So the condition here is heated iron reacting with excess air to form triiron tetraoxide, and the balancing is going to remain according to the same principle. You start by balancing the metal, you go balance to the oxygen, and you're going to get triiron tetraoxide as required in any of the questions that you'll be attempting. So let's look at the reaction of iron with acids. Now first of all, iron reacts with dilute acids, and it reacts with the cold dilutes as the condition. So iron reacts with cold dilute sulfuric acid and hydrochloric acid. Now hydrochloric acid, remember that in the previous video I told you it's a non-oxidizing acid. So that means that it can, if at all it's concentrated, it reacts in the same way like its dilute. But sulfuric acid is an oxidizing acid when it's hot concentrated, but it's a non-oxidizing acid when it's dilute. So that's why we specify that here reacts with cold dilute sulfuric acid and hydrochloric acids. I say that hydrochloric acid because hydrochloric acid is a non-oxidizing acid both in its concentrated and in its dilute format. So when it reacts with dilute sulfuric acid and both concentrated and cold dilute hydrochloric acid, it forms hydrogen gas and then the corresponding ion to salts. Let's look at the general equation that can represent that. So in the general equation, you're simply going to say that iron as a solid reacts with any of the dilute acids, cold dilute sulfuric acid, or both concentrated and dilute hydrochloric acid, forming ion to salts and then together with hydrogen gas. Now proceeding, I'm going to say that iron reacts with dilute nitric acid, forming a mixture of products. Now remember that I told you nitric acid is an oxidizing acid, whether it's dilute or it's concentrated. So this is a redox reaction, and I've over mentioned about redox reactions. I previously uploaded a video talking about balancing of redox reactions, and I made it elaborative. So make sure that you try out all these examples, all these equations, and you see how the balancing came about using that knowledge. The video is just 10 minutes long, so I'm just going to go through it. So if you look at this equation, iron was oxidized to iron to nitrate by this dilute nitric acid. But nitric acid, after oxidizing, it got reduced to ammonium nitrate together with water. So you need to make half equations. One half equation is going to be iron being oxidized to iron, and then the other half equation is going to be nitric acid getting reduced to ammonium ion plus water, and that's your half equations which you need to balance. Now proceeding, we are going to say that concentrated acids, we are going to look at the reaction of iron together with concentrated acids. Now I'm going to say that hot concentrated sulfuric acid, remember that I told you when sulfuric acid is hot and concentrated, it acts as an oxidizing agent. So the condition here for this equation here is going to be that hot concentrated sulfuric acid is going to oxidize our iron to iron 3 sulfate. Now remember that we didn't oxidize it to iron to sulfate because iron 3 sulfate is the most stable as compared to iron to sulfate. Whenever we are reacting anything with a strong oxidizing agent, it oxidizes it to the element's most stable oxidation state, and the most stable oxidation state of iron is +3. So hot concentrated sulfuric acid oxidizes iron to iron 3 sulfate, and then the acid after oxidizing, it gets reduced to sulfur dioxide together with water. So iron as a solid reacts with hot concentrated sulfuric acid to give us iron 3 sulfate, sulfur dioxide, and water. Like I said, this is also a redox equation. Just like I said that I made a 10 minutes video explaining how these equations can be made. So I hope no one still has a concern about balancing these equations and how to know how to balance them, because I made a well-elaborated video putting into details everything you need to balance such equations. So iron as a solid reacts with hot concentrated sulfuric acid to give us iron 3 sulfate, sulfur dioxide together with water. The oxidizing agent is sulfuric acid. After oxidizing, it gets reduced to sulfur dioxide gas together with water. Iron gets oxidized to iron 3 iron. So those are your half equations. You try to balance them and you combine them, and you see how the balancing of this equation came about without stressing any of your efforts. Now let's go to the reaction. Now with concentrated nitric acid, I want you to understand this. Concentrated nitric acid, when nitric acid is concentrated, it's rendered passive to almost every transition element. Reason being is that because of their high charge densities as ions, so we do not, majority of the transition elements consider or they render concentrated nitric acid passive. They do not have reactions with concentrated nitric acid. So that this should be at the back of your mind. Majority of the transition elements do not react with hot concentrated nitric acid, and it's the main takeaway about these reactions under concentrated acids. Now, so let's go to the reaction of iron together with nonmetals such as sulfur. Now here we are going to say that when a mixture of iron and sulfur is heated together, a red glow is observed and a black solid is formed. Now here we are giving an observation, but when I'm making a statement, we just need conditions. So you just say that heated iron reacts with heated sulfur to form iron to sulfate. As simple as that. But when you ask for observation, then you can, when you ask for observation in the questions, you only talk about the color changes. So that will be a red glow forming a black solid. That's the case of observation, but in writing an equation, we do not want color changes. We only want name of the conditions and then the name of the products. So I hope that is very elaborative. So hot iron reacts with hot sulfur to give us hot or black iron to sulfate. All of them, both the reactants and the products, existing in solid states. Now, the other nonmetal we are going to look at is going to be with chlorine. So we are going to say the same conditions. Heated iron reacts with dry chlorine gas to form iron 3 chloride. This is a very elaborative way you should present your statement before giving an equation. So iron reacts with chlorine to give us iron 3 chloride. Now remember that here, iron is a solid and chlorine is a gas, and also iron 3 chloride, which is being formed, is going to be a solid. Now let's look at the other element, which is going to be hydrogen chloride. Now this is a very common element. Whenever there are two types of chlorides of iron. We have iron 2 chloride and iron 3 chloride. Chlorine is a strong oxidizing gas. So whenever we use chlorine, whenever we heat iron with chlorine, we get the one which is most stable, which is iron 3 chloride. But for us to get iron 2 chloride, we need to react iron, or we need to heat iron with a non-oxidizing gas, but which will give us iron 2 chloride, and that is hydrogen chloride. So hydrogen chloride, since it's a non-oxidizing gas, we easily heat it with iron for us to get our product which we need of iron 2 chloride. And it's a very common question in UNEB, because majority of the students, you react iron together with chlorine, forming iron 3 chloride, which is not the case. So you need to be very careful. Chlorine is a strong oxidizing gas, so it will always give you iron 3 chloride. For us to prepare iron 2 chloride, we use dry hydrogen chloride gas. So you need to pay very close attention to that. So we're going to say that heated iron reacts with dry hydrogen chloride gas, forming iron 2 chloride together with hydrogen gas. So the equation is going to be as follows: iron reacting with hydrogen chloride to form iron 2 chloride together with hydrogen gas. We form iron 2 chloride because hydrogen chloride is a non-oxidizing gas. But when you heat iron directly with chlorine, we form iron 3 chloride because chlorine gas is an oxidizing gas. So it oxidizes iron to iron 3 to the oxidation state of +3. But hydrogen chloride, since it's a non-oxidizing gas, it oxidizes iron to iron 2 chloride, since it's a non-oxidizing gas. So balance the equation, you follow the same procedures. Balance the metal first, balance the chlorine, and then lastly you balance the hydrogen atoms. Lastly, now having looked at the reactions that are involved with iron, let's look at the compounds that can be formed by iron. Now before looking at the compounds, let's talk about the variability of the oxidation state. Why is the +3 oxidation state more stable than the +2, and how do they come about? So we're going to say that the principal oxidation states of iron are going to be the +2 together with the +3, and then the loss of the 2 electrons from the 4s orbital or subenergy level is going to give the iron to iron. So we already talked about this earlier. So that's why we are having iron to iron. It's due to the loss of 2 electrons from the 4s subenergy levels. Then while the loss of 2 electrons from the 4s and together with 1 electron from the 3D subenergy levels or orbital is going to give the iron 3 ion. So the reason why the plus 3 is more stable than the plus 2 is because the 3D orbital is going to be half filled when present in the iron 3 ion, and the compounds therefore are going to be more stable as the compounds that are going to be formed in the iron 2 ion. Because if you look at the iron 2 ion, the 3D subenergy level is neither going to be half filled nor fully filled. So that means that, and we say that for an energy level or for a subenergy level to be thermodynamically stable or more stable, it has to be either halfly filled or fully filled. So since in the iron to iron, the 3D orbital is neither of the two, it makes the plus 2 oxidation state in iron to be very unstable, and therefore compounds of iron present in the plus 2 oxidation state are going to easily be oxidized to the plus 3 oxidation state, because in the plus 3 oxidation state is where we are having our 3D subenergy level to be halfly filled. So compounds that are present in the plus 3 oxidation state of iron are going to be more stable as compared to the compounds that are going to be formed in the plus 2 oxidation state of iron. So we can conclude by saying that this is why iron 2 compounds are easily oxidized to iron 3 compounds, due to that explanation I've just gave right there. Now let's start with the iron 2 compounds. So iron 2 compounds, we're going to start with iron 2 oxide. Now let's look at how it is formed and which elements can we achieve it from, together with its reactions. So we're going to say that iron 2 oxide is a black solid that can be obtained by heating iron 2 oxalate in absence of air. So this is a very important condition, that we can only do this in absence of air. And when you do so, you get iron 2 oxalate. I told you whenever you heat an oxalate, the first gas you give off is going to be carbon monoxide gas. Now after carbon monoxide gas leaving, you remain with iron 2 carbonate. When you heat iron 2 carbonate, we say that whenever you heat any carbonate present in the plus oxidation state, you are going to form an oxide together with a carbon dioxide gas. So whenever you heat any oxalate, the first gas you obtain is carbon monoxide. You'll be remaining with a carbonate that is going to give you carbon dioxide gas together with an oxide. And that's how you can master reactions of heating oxalates. The other condition is going to be that iron oxide is we say that it's a black solid and it's a basic solid, and therefore, being basic, it reacts with dilute acids, forming iron 2 salts together with water. So iron oxide reacts with dilute acids and hydrochloric acids to form iron 2 salts together with water, just like any other oxide present in the plus 2 oxidation state. Now let's look at the hydroxide or the iron 2 hydroxide. We are going to say that it can be obtained as a green precipitate by adding an alkali such as sodium hydroxide to a solution containing iron 2 salts. But notice that this one is always temporary. You have done this practically, whereby usually in the laboratory you are going to get a darker green precipitate. But this darker green precipitate always turns brown on standing. I hope you have been evidencing that right away from your O-level, because this is a very common question in O-level. So iron 2 ion reacts with hydroxide ions from an alkali to give us iron 2 hydroxide, which is a darker green precipitate. So we're going to proceed and say that it is basic, and therefore it's going to react with dilute acids to give us iron 2 salts together with water. So iron 2 hydroxide, being basic, reacts with acids, giving us salts of iron 2 or salts that are present in the iron plus 2 oxidation state, and also giving water as another product. But I've told you that whenever you are forming an iron 2 hydroxide in the laboratory, it's always given as a darker green precipitate, which is always going to turn brown on standing, because the plus 2 oxidation state in iron is very unstable. Now looking at the next reaction you have already talked about it, which was iron 2 chloride. And here we're going to say that anhydrous iron 2 chloride is a pale yellow solid that can be prepared by heating iron in a stream of dry hydrogen chloride gas. And I've already explained this equation, and I've told you why we cannot prepare iron 2 chloride using chlorine gas directly. So since we have already explained it, let's just proceed. And we say that hydrated iron 2 chloride is obtained by crystallization method. Now this is usually done in the laboratory analysis or laboratory preparations. Now let's look at the individual procedures by which you can prepare hydrated iron to sulfate. So we're going to say that in the laboratory, because that's where the such reactions are made, it is going to be prepared by the action of dilute sulfuric acid on iron fillings and the crystallization of the salt from the solution. So the first reaction is going to be getting your iron fillings, and then you react it with warm dilute sulfuric acid. Now when you react iron 2, or the iron as an element, with warm dilute sulfuric acid, we are going to form iron 2 sulfate together with hydrogen gas. Because we say that whenever you react an element with an acid, if at all it's an element with an acid, you get a plus oxidation plus 2 salts, which in this case is going to be iron 2 sulfate, and then the hydrogen gas. So after getting your iron 2 sulfate, it's going to react with the water which is coming from the environment. These are formed as crystals. So it's going to absorb water from the environment, and then it gives us what we call the hydrated iron 2 sulfate, or which can also be called iron 2 sulfate 7 water as another name. And you are putting here solid because after absorbing water, it's going to become crystals, and crystals are solids in nature. So proceeding, we are going to say that hydrated iron 2 sulfate decomposes when heated, first to white anhydrous iron 2 sulfate. Now usually these, like I said, these are laboratory examination practices. They will give you a solid wire, and then we tell you to heat, and then you start to mention what is being observed. So whenever you're having any solid, let me say in qualitative analysis under inorganic chemistry, question number 2 in your practicals, you are told to heat. Whenever you obtain any mode of crystallization, we expect that the solid you are dealing with was hydrated. So you take a colorless condensate on the upper parts of your test tube, which is water of crystallization. Or you simply say that your solid, or the component or the substance you are dealing with, was simply hydrated. So whenever you heat such hydrated compounds, the first thing to do is that the water has to first get off as a colorless condensate, and then you remain with the main component which is present in that hydrated salt, being anhydrous. So antisulfate when it's anhydrous is white in nature. Now further or strong heating is going to cause decomposition of iron 3 oxide. Decomposition of iron 2 sulfate to give us iron 3 oxide together with sulfur dioxide gas and then sulfur trioxide gas. Now this question is very common. Under mock examinations, because majority of you forget that whenever you heat an iron to sulfate, we get both oxides of sulfur, which is sulfur dioxide and sulfur trioxide. Now being the case, the mock examination bodies also want it the most to be examined whenever they set about iron. So if you're writing these notes down, you make sure that you put a scientific note, or you bold this equation, or you put a reminder for you to be glancing at this equation whenever you come across it. That whenever you're heating iron to sulfate, you always obtained iron 3 oxide together with sulfur dioxide gas and sulfur trioxide gas. Now, having looked at the compounds of the plus 2 oxidation state of iron, let's look at the compounds of the plus 3 oxidation state of iron. So here we are going to start with iron 3 oxide, and we are going to say that iron 3 oxide, remember that it's the same as hematite, but it's just that hematite is contaminated with other impurities. So we're going to say that iron 3 oxide occurs as hematite in nature in presence of the ore, and in the laboratory it can be prepared as a brown solid by heating both iron 2 sulfate together with iron 2 hydroxide. Now remember that you have already looked at the heating of this. Whenever you're heating iron 2 sulfate, you always get iron 3 oxide, and you form 2 oxides of sulfur. One of them is sulfur dioxide and the other one is sulfur trioxide. Balancing, I told you, start with the metals. So if you look here, iron is 2, that's why I placed here 2. And if you consider the other balancing, you find that the equation is going to be self-balanced after that. And that's the main part, or that's what makes chemistry interesting. The moment you master equation balancing, or you'll be left with mastering what is just being formed. You just need to know the conditions and the products. But balancing is as easy as required if at all you're a student who is present on this channel. So iron trioxide can also be heated to give us what we need, which is iron trioxide. And whenever we heat an hydroxide, we always get steam, or which you can write it as water. So steam together with an oxide whenever you heat an hydroxide. So heating iron hydroxide, which is a reddish brown solid or a brown solid, you are going to form your brown solid of iron trioxide and water or steam, because heating is involved. When you're heating, always water evaporates, which becomes steam. So the most correct student will be the one that writes the symbol or the state of water to be in terms of steam, since we have heating going on. So you're going to say that also anthioxide is a basic oxide, and therefore, being basic, it readily reacts with hot dilute acids to form iron 3 salts together with water. Just like any other oxide, whenever iron oxide or iron 3 oxide reacts with an acid, we are going to form iron 3 salts together with water, and we shall look at the examples under that. Now proceeding, we are going to be looking at the chemistry of iron 3 hydroxide. Now for iron 3 hydroxide, it's going to be formed simply by adding an alkali to any solution that is containing iron 3 salt. So to a test solution containing iron 3 ions, when you add, let me say, sodium hydroxide, the hydroxide ions from sodium hydroxide react with the iron 3 ions present in that test solution, giving us a brown solid or a brown precipitate known as iron 3 hydroxide. So it's also basic, and therefore, being basic, it easily reacts with dilute acids to give us iron 3 salts and water, which we have already mentioned earlier on. So an hydroxide reacts with water being basic, reacts with acid being basic to give us source of iron 3 together with water. Now notice that when we're having iron as an element reacting with acids, we form salt together with hydrogen gas, but when you're having an oxide or an hydroxide reacting with an acid, we form water together with the salts. So you should take note of that as you are taking your revision. So looking at iron chloride, which is another element, we are going to say that anhydrous iron chloride is prepared as a black sublimate by passing dry chlorine gas over heated iron ore. So the good statement for this equation would say that heated iron reacts with dry chlorine gas to give us iron chloride. And here we don't form iron chloride because I told you iron chloride is formed by hydrogen chloride gas since it's non-oxidizing. So chlorine being an oxidizing gas is the one which gives us iron chloride. So iron reacts with chlorine, or it reacts with iron reacts with chlorine gas or the high oxidizing chlorine gas to give us the iron chloride, giving it its most stable oxidation state of the +3 of iron. So I'm going to say that, however, this iron chloride is going to be a covalent solid as it's a dimer, and it's going to exist as this in vapor phase. Now the reason for that, we looked at this under structure and bonding, the first video where we talked about polarizability, and we said that if you're having an ionic compound but one of the cation having a high charge density, we expect that such a compound is going to undergo polarizability, and I explained the effect of polarizability on these compounds in depth. So the reason why this is existing as a dimer is because of polarizability. And if you want to get more deeper explanations under that, you refer to the video that we made under structure and bonding explaining polarizability. You'll be understanding it in details. And if you're still having any issues, you try to reach your concern out so that it can be addressed. Now looking at the hydrolysis of iron 3 salts in water, we are going to be looking at the following. Now remember that I told you that when you're doing with, or when you're studying about salt hydrolysis, which is also a separate video, but the salt hydrolysis I think is under ionic chemistry videos in the physical chemistry playlist. I talked about salt hydrolysis in details. This one for inorganic chemistry is just giving you a review about it. And I told you the general equation, the final general equation must be a solid being formed. So usually, solutions containing iron 3 salts are acidic in nature, and the reason for this is due to salt hydrolysis of this hydrated iron 3 cation. And the hydrolysis is as a result of the following, and it said that there are 3 reasons. One of them is high charge density, the other one is going to be small ionic radius, and then the other one is going to be a large ionic charge. So I'm going to say that this, due to the high charge density, this becomes heavily hydrated in solution, and the coordinating water molecules are going to be highly polarized, weakening the oxygen to hydrogen bond, so that the protons can easily be released in solution, making it acidic. Now, there are a series of equations. This is just one of the equations of hydrolysis. By the final equation of hydrolysis, we end with a solid, a hydrated solid of iron. And I said that this is just a review about what you covered. But the main equation that you need, or the main concepts of hydrolysis that you need, are present in the video of ionic equilibria, and it was named salt hydrolysis. That's why you get the elaborative explanation of these statements. The good thing is that I mentioned everything together with the guiding questions on how you can be approaching each of them. Now let's just go to the another concept. Like I told you, you go back to the salt hydrolysis video and ionic chemistry or ionic equilibrium, and then you see the salt hydrolysis in details. So let's first look at conversions of iron 2 to iron 3. Now we're going to say that the green solution turns to yellow. We are saying that the green, this is due to iron 2. Iron 2 compounds are green in nature. Yellow or brown is for iron 3 compounds. So green solutions turn to yellow whenever you are converting iron 2 compounds to iron 3, and this is due to oxidation of the iron 2 to get iron 3 ironed compounds. So one of them you are going to, that means that for us to increase oxidation state, that means that we need to deal with oxidizing agents. But remember that wherever we are having oxidizing, we are also having reduction, and therefore majority of the concepts or majority of the reagents that you're going to be dealing with are going to be redox reactions. And I've already said that I've already made a separate video explaining redox reactions. So that means that I'm just going to go over these ones as quickly as possible. So whenever you're having acidified potassium permanganate, it can easily oxidize. So the general observation is green solution turns to yellow. And the reason is oxidation of iron 2 ions to iron 3. So that's the general explanation for all these reactions that you're going to be looking at. So acidified manganate 7 reacts with iron 2 and it oxidizes it to iron 3 ions, and after it oxidizing, it gets reduced to manganese 2 ion together with water. And the same applies to acidified dichromate 6, which is the commonly used reagent in organic chemistry. So acidified dichromate 6 oxidizes iron to get iron 3 ions, and it after oxidizing, it gets reduced to iron 3 chromium 3 ions together with water. Just like I said that these are redox reactions, we have already covered majority of them, and I hope each of you at this platform is now very okay with balancing these equations. Now the next reaction is going to be using hydrogen peroxide. Also hydrogen peroxide in acidifying medium acts as a strong oxidizing agent. So hydrogen peroxide oxidizes iron to iron 3 ions. Now after acidified hydrogen peroxide oxidizing, for it only gets reduced to water. So you balance up the two equations and then you get your redox equation having the following components. So the other one is going to be chlorine. Now remember that I told you that chlorine is a strong oxidizing agent. Same applies to bromine. So chlorine or bromine, when it's added to a solution containing iron to salt, acidified together with the sulfuric acid, still we are going to have the color change. But here the color change is going to be that of halogen, which you are going to note the most, since it's the one you're adding. So chlorine, which is a yellow-green gas, dissolves in a solution containing iron to ions, forming a brown solution. So it will turn from green to brown due to oxidation of the iron to iron compound to iron 3 iron compound. And then chlorine after oxidizing, it gets reduced to the chloride ion, which is the same applies to bromine. So bromine dissolves, so the brown color of bromine will disappear, forming brown color of bromine will disappear, or bromine will turn colorless, and then the solution will slowly fade from green to brown or yellow due to formation of iron 3 compound, and the bromine after oxidizing, it gets reduced to the bromide ion. So with acidified potassium permanganate, which we have earlier looked at, which we started with. This is a repetition. So we started with these two, and we looked at what they give earlier on. Now let's look at the conversions that are going to be involving from iron 3 ion to iron 2 ion conversion. So here we are going to be looking at the oxidizing properties which iron 3 ion has in a test solution, and here we are just going to be adding other reagents containing anions of which iron 3 cation can oxidize. So if you start with the reagent of potassium iodide, you look at that iodide ion is going to react with the iron 3 ion, and after that iron 3 ion is going to be reduced to the iron 2 ion, and the iodide ion is going to be oxidized to iodine. Now since iodine is brown in nature, we shall say that the solution, or the Curry solution, or the brown solution is going to, remember that we may have a Curry solution containing iron 3 ions, and you may say that that solution is going to form a brown solution due to formation of iodine. So going to the oxidizing property of part B, we are going to look at usage of hydrogen sulfide. Now usually we say that you avoid the word deposit, you instead use solid or precipitate. So a yellow solid of sulfur is going to be observed when you react hydrogen sulfide together with iron 3 cation, because the iron 3 cation is going to oxidize the sulfide ion in hydrogen sulfide, giving us the sulfur as a solid, and sulfur as a solid exists as a yellow precipitate or a yellow solid in solution. So iron, after oxidizing, it gets reduced to the iron 2 ion, and therefore we are going to say that the solution turns from brown to green because the iron 3, which was making the solution brown, results into formation of a green solution due to formation of iron 2 ion compound in that solution. So an alternative operating that equation can be as follows. Now let's look at the usage of sulfur dioxide. Iron 3 cation also oxidizes sulfur dioxide to get a sulfate ion, and after oxidizing that, protons are going to be coming from water after its oxidizing property. So we're going to say that a yellow solution, a brown solution, turns green, and this is due to iron 3 ion being reduced to iron 2 ion oxidation state in the solution. So we're going to say that iron 3 ion are going to oxidize the sulfur dioxide, and sulfur dioxide, after being oxidized, we are going to get the sulfate ion, and then later the iron 3 ion gets reduced to iron 2 ion together with formation of protons, and these protons are going to be coming from this water. Like I told you, these are redox reactions. You will easily be seeing how this balancing comes about if at all you mastered redox equations, just like I've been emphasizing in the previous videos. Now let's look at the qualitative analysis of the two different ions. So you're going to start with the iron 2 ion. So some of the preliminary reagents we have in sodium hydroxide together with ammonia, and they all give the same observation together with the same equations. So we're going to first go through one because they give the same observation and same equations. So we're going to say that a green precipitate is soluble in excess, which turns brown on standing. And the explanation for turning brown on standing is going to be due to oxidation of the iron 2 hydroxide, which is being formed, to iron 3 hydroxide, and this is done by area oxidation or by atmospheric oxygen. So the first equation is going to be iron 2 ions in the test solution reacting with the hydroxide ions, and this they're going to be forming the iron 2 hydroxide, which is a green precipitate, and in the laboratory you obtain it as a darker green precipitate. But this darker green precipitate undergoes area oxidation by atmospheric oxygen to give us the iron 3 hydroxide, which is a brown precipitate that is formed on standing. Now the observation for you when you're using these two preliminary reagents, both aqueous ammonia and sodium hydroxide solution, is the same. So you don't have to repeat about explaining anything. Same equations and same observation. Now proceeding, this is the third component is going to be our confirmatory reagent for the iron to iron. Now notice that what is going to vary, both iron to iron and iron 3 ions have quite the same have quite the same conformatory reagent, but what varies them is the oxidation state. The iron to iron is confirmed by potassium hexacyanophenate 3. So the oxidation state in this complex is 3. And they all give us the same observation. Whenever you're confirming iron, we see a dark blue precipitate. So the equation is going to be as follows, which is also going to give us a complex, but this complex is due to formation of a dark blue precipitate, which is given by this formula. So we look at the qualitative analysis of iron 3 cation 2, and it also has preliminary reagents, which are sodium hydroxide and aqueous ammonia, and both of them, they give us the same observation. So we're just going to go through one. So we're going to say that the observation when you add either of these reagents is that you're going to say brown precipitate, which is insoluble in excess, and that is due to formation of iron 3 hydroxide as a result of the reaction between the iron 3 cation together with the hydroxide ions coming from either sodium hydroxide or ammonia solution or aqueous ammonia, giving us similar observations. Now let's go straight out to the confirmatory reagent. So the confirmatory reagent is either potassium hexacyanophenate 2 solution or it's either potassium thiocyanate solution. But usually we consider this one. For iron 2, remember that I told you they vary by oxidation, but they have the same names. For iron 2, we used hexacyanophenate 3. For iron 3, we used hexacyanophenate 2 solution. And they all give us same observation, which is a dark blue precipitate. And the equation is as follows, forming a complex which is a dark blue precipitate. However, if you use potassium thiocyanate solution, which is a commonly asked reagent in paper 1, you're going to observe a dark red solution or a dark red coloration, and that's due to formation of a complex of iron thiocyanate. So iron reacts with the thiocyanate ion to give us this complex, and this complex is what causes the formation of the red coloration. Now this brings us to the end of this video. You're advised to like the video, share it to your friends, and make sure that you all benefit together. Always address your concerns in case you don't understand my approaches in the comment section so that I try to elaborate more about the areas in which you have not got the explanations.